Hello and welcome to a video on the fundamentals of probability. In this video we're going to compute theoretical and empirical probability. So what is probability? It is a measure of likelihood that some event will occur. And we have a scale that goes from 0 to 1 typically, or if we write it as a percent, 0 to 100%. And 0 means that an event is impossible, it can't happen, all the way to 1 being a certainty that an event will happen. Alright, and the higher the probability, the closer it is to 1, the more likely. The closer it is to 0, the less likely. Alright, some vocabulary. When we are discussing a probability, you'll hear me say things like an experiment. And that's just anything that we do which we don't know what's going to happen, what the outcome is going to be. Alright, the sample space, that means all the things that could possibly happen as a result of an experiment occurring. We use S to represent the sample space, and we typically write that in set notation. We'll say S equals, and then we'll put a little set bracket, and then we'll just list things that could possibly happen. Alright, and then event E is any subset of the sample space. So if S was 1, 2, 3, something like that, then one possible value for E could be 1 or 2 or 3. It could be any one of the things that could happen. And it could also be more than one thing. It could be 1 and 2, or 1 and 3, or 2 and 3, and so on and so on and so on. Okay, it could be any combination, subset of the sample space. Right, it could be none of the possible outcomes. None is a possible outcome. So the sum of the theoretical probabilities must always be 1. Okay, so you can have like a probability of a third, a third, a third, probability of like 1/2, 1/4, 1/4. It just all has to add up to 1, whatever the likelihood of each one of the possible events are. Alright, now if we want to compute theoretical probability, then the theoretical probability is some of an outcome E. In E is the notation that this is what we mean the number of ways that E can happen. That's what this means. The number of equally likely outcomes that satisfies event E. Alright, the sample space has in S total outcomes possible. Alright, then the theoretical probability is the number of outcomes in event E divided by the total number of outcomes. Okay, you can think of it as the number of ways E can happen, and then you divide that by the total number of things that can happen. Okay, so that's the way we think of the probability of E occurring. So just to give you a concrete example, if E were the number of ways that I could draw a king, if I'm going to draw a card off of the top of a regular deck of cards, what's the probability I draw a king? Well, it's the number of ways I can draw a king divided by the total number of cards that I could have drawn. So there are 4 ways to draw a king. There's a king of hearts, king of diamonds, king of clubs, king of spades. That's 4. And then there's 52 total cards in a deck. Alright, so that 4 out of 52 reduces to a 13th. Alright, so that's what we mean by a theoretical probability. You count up how many ways whatever it is that you're trying to find can happen, and you divide by the total number of possible outcomes. Okay, so this NE is the 4, this NS is the 52, and then you always reduce these when you're done coming up with the initial fraction. That's just the counts over the counts. Alright, this notation, the P stands for probability. This is the event, so the probability of event E. Alright, let's look at an example. We roll a single die. Alright, 6-sided die. When you see this 6-sided, when you see that we roll a die, just assume that it's 6-sided. And we want to find the probability that we roll in part A a 3, and in part B an even number. Okay, well the sample space here, S, all the things that could possibly happen, I could roll a 1, a 2, a 3, 4, 5, or a 6. Okay, and then how many of these possible outcomes are a 3? Just one, that one right there. So there's only one way to roll a 3, so the numerator in our fraction from the last slide is equal to, this one, is equal to 1. And because there are 6 possible outcomes, the denominator is 6, so 1/6 is our probability. All right, and sometimes it won't reduce, sometimes setting it up is the answer. Now to roll an even number, I could roll a 2, a 4, or a 6. And so since 2, 4, 6 are the possible outcomes, there's 3 things that satisfy the event of an even number. So 3 over 6. So still just 6 possible outcomes, just whatever number could show up on the die. And then the 3, the numerator, is coming from the fact that there's 3 even numbers. That does reduce to a 1/2 though. Make sure to reduce. Okay, don't just leave it in that form or you won't get counted credit. Alright, you might get a little tiny bit of partial credit if it happens on a quiz, but you won't get any full credit for it. Okay, and you definitely will have to redo it on your homework. Don't send me a homework link saying, I didn't reduce, can you give me partial credit? Because I'll say just click similar exercise and do it again. Okay, but on a quiz, if that happened, then let me know and I'll give you a tiny, again, it's not going to be a lot of partial credit, not even going to be half credit. But I'll give you a tiny little bit of partial credit for setting it up correctly but not reducing. Alright, if you're dealt one card from, there's our standard 52 card deck. Find the probability we're dealt a kings, that's the one we did before. Right? Or a heart. Now a heart, remember that's a suit. And there are 13 cards in each suit. Okay, if you don't know the standard deck, do a Google search for a standard deck of cards and just look on images even and you can get your standard deck. So here is ace all the way through king in all 4 suits. So you can have that. And you may want to print that out if you're not familiar with it, because there are a lot of those types of questions. Here's one that's got the suits and the names on there. But there are going to be a lot of questions in dealing with cards when you're doing this initial probability section. So it wouldn't be a bad idea if you don't know the standard deck to print this out so you can do a little counting with an actual picture rather than having to count it up in your head. Alright, but anyway, on this problem there were hard outcomes and total possible outcomes. So there's 13 total possible outcomes, but then there's the hearts, so you could count them. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, including the face cards. So 13 out of 52. So it wouldn't be a bad idea to have that, again, if you don't know your standard deck all that well, if you're not a card player. Alright, empirical probability. This is different than theoretical probability in the fact that we estimate the probability. It's really an estimation of a probability. So we're saying that the probability that an event occurs is approximately the number of times we've seen the event occur divided by the total number of observations. So let's say that I've drawn a card off the top of a deck of cards 100 times. So that would be our denominator, total number of occurrences, total number of trials of flipping a card over. And let's say that in total number of times that I've gotten 6 kings. So I've got 6 kings out of 100 tries. So what we're saying the probability of getting a king is 6 out of 100, which would be the same thing as 3 out of 50, right? Which is 0.06 if we wrote it as a decimal, or 6%. Alright, well, we just found the theoretical probability, which is the probability that the probability of a king is 4 out of 52 or 1 out of 13. Alright, 1 out of 13 as a percent, 1 divided by 13 is 0.077 roughly. So if I did times 100 to get to a percent, so about 7.7%. But just trying it 100 times, we're getting around 6%. So 1 is the theoretical probability. This is the probability that we get a king. 1 is doing experimentation, and this is what we get when we're doing the probability of a king via just repeated trials, trying to estimate what it would be just by doing it over and over and over again. Alright, now there's this idea called the law of large numbers. If you Google the law of large numbers, you would see it's the idea that as you do something over and over and over again, the probabilities may go crazy initially, but eventually it levels off. Alright, that we end up with, as we do this thing, notice the number of trials here, there's 100. Alright, we're all the way up here to 1,000. This is the theoretical probability, alright, and notice the other value approaches the empirical probability. The number of trials and everything increases. We approach that theoretical probability and kind of hone in on it. So the law of large numbers says that if you do this enough, if you make your number of trials, repeated trials, high enough, if this ns gets really large, then the probability empirically will get closer and closer and closer to the theoretical probability. Alright, so that's called the law of large numbers. They basically will match that this probability of drawing a king, if I keep doing it, if I instead of stopping at 100, if I just kept flipping over the top card on a deck of cards and shuffled and shuffled and every single time and just kept doing it, that eventually I would get 1 out of 13 or 4 out of 52, that 7.7% as the empirical probability. It would get closer and closer to that. Alright, another example from a table. You'll be expected to be able to pull off probabilities from a table in this solution. But the question says if one person is randomly selected, alright, from this population described above, from this 242 people, 242 million people, this is actually millions, we want to find the probability the person was a female. Okay, so the probability of selecting a female is observed by the number of females, which is this over here. Alright, not this. This is just married females. So you go all the way over here to total females, and then we divide by the total number of adults that were in our population, which again total is over here. So that's where these numbers are coming from. There's the 242. There is the 124. Now these are in millions, but the millions would divide out, so we can just use the numbers from the table. So divide those two, we get about 0.51 for the probability, a little bit more than 50-50 chance.